Okay, let's dive right in. We're going to be talking about a question that is, frankly, singular and terrifying. It's the question that really underpins the entire world we live in. Can a launched nuclear missile actually be stopped?
It's the ultimate high-stakes question, isn't it? It's been the foundation of geopolitics for, what, almost 80 years now?
Right.
Because the second you even ask, can we intercept it, you're already admitting that a much bigger failure has happened. Someone, somewhere, has already made that catastrophic choice to launch.
Exactly. And that's really our mission for this deep dive. This isn't just going to be a technical rundown of missile defense systems. We're going to explore the physics that created the weapon, the history that shaped our response to it, and really the human element, the decision-making that keeps us teetering on this brink.
It's a topic that demands a really calm, thoughtful approach. We're not here to rehash fear. We're trying to understand the incredibly delicate balance we live in, a balance that's, constantly being tested by new technology and politics.
So where do we begin? I think it has to be with the fundamentals, the mechanics of it all.
Absolutely, the mechanics of mass destruction.
Let's start there. For anyone listening, when we say nuclear missile, what are we actually talking about? The terms get a bit blurry.
That distinction is vital. It's really three core parts. First, you have the missile itself. That's just the delivery system. Think of it like the ultimate high-speed cargo plane.
The carrier.
The carrier, exactly. Its job is just to get from point A to point B. The second part is the nuclear warhead. That's the package. That's where the unimaginable destructive force actually comes from.
And the third piece, the one people often forget.
The guidance system. It's the brains of the operation. It's what makes sure that carrier, that rocket, actually hits its target with, terrifying precision. Without it, you just have a very big, very dangerous firework.
And the power source behind that warhead is what separates it from anything else in human history. We're not talking about chemical explosives like dynamite.
No, it's not even in the same ballpark. The difference is almost nonsensical. Chemical reactions like in TNT, they just rearrange electrons between atoms. It releases energy, sure, but it's limited.
But nuclear weapons?
Nuclear weapons tap into the forces inside the atom's nucleus. That's a whole different order of magnitude.
And that happens in one of two ways, right? Fission and fusion.
That's right. Fission is the process of splitting a heavy atom, usually uranium or plutonium. One atom splits, releases a huge amount of energy, and throws off neutrons that hit other atoms, which then split, and so on.
A chain reaction.
A chain reaction. That's what the first atomic bombs use. But then you have fusion.
The H-bomb.
The hydrogen bomb, or thermonuclear weapon, yeah. Fusion is the opposite. It's forcing light atoms, like hydrogen, together under immense pressure and heat. It's the same process that powers the sun.
And to get that process started, you basically need to set off a smaller fission bomb first.
Exactly. It's a two-stage process. The fission bomb acts as the trigger for the much, much larger fusion reaction. And the result of both is just this vast release of energy in a fraction of a second.
And that energy release creates a cascade of lethal effects. It's not just one big explosion.
No, it's a devastating combination. First, there's the extreme heat, an incredible flash that vaporizes everything at ground zero and can cause third-degree burns miles away.
Then the shockwave.
A supersonic blast of air pressure that just flattens cities. Then the prompt radiation, which is instantly lethal to anyone nearby.
And after all that, there's what's left behind.
The residual radiation, the fallout. It gets carried by the wind for hundreds, even thousands of miles. It poisons the air, the water, the soil for years, decades. It's a combination of that immediate city-killing power and the long-term environmental poison that makes these weapons truly civilization-ending.
So let's trace the path of one of these things, an ICBM, an intercontinental ballistic missile. We said it was like a cargo plane, but it goes much higher, much faster.
Oh, absolutely. It starts with the boost phase. The engines fire, lifting this massive rocket out of the atmosphere. That only lasts for a few minutes.
Okay.
Then comes the mid-course phase, the longest part of the journey. The missile is just coasting silently through the vacuum of space. This can last 20, maybe 30 minutes.
And during this phase, the warhead separates from the rocket.
That's right. The warhead, maybe along with some decoys we'll talk about later, separates and begins its descent. And that's the final part, the terminal phase. It screams back into the atmosphere, accelerating towards its target.
And it's crucial to remember, the detonation, the nuclear explosion, doesn't happen during the flight. It's programmed to happen at the destination.
Its only job is to survive the trip and go off at the precise time and altitude.
To really understand the gravity of this, we have to go back to its birth, the Manhattan Project.
An undertaking unlike anything before it. From 1942 to 1945, the US, the UK, Canada, they employed hundreds of thousands of people in total secrecy, building entire cities like Los Alamos out in the desert.
And the scientists involved, Oppenheimer, Fermi, these giants of physics, they weren't just driven by curiosity. They were driven by fear.
And that's the key. Absolute existential fear. Many of them were refugees who had fled Europe. They knew the physics was possible, and they had every reason to believe that Nazi Germany was trying to build a bomb too.
So the motivation wasn't to gain a weapon of ultimate power, but to stop Hitler from getting one first.
It was seen as a necessary evil, a race to save the world from a terrible fate.
But then, the pivot, the moment that changed everything.
Germany surrendered. May 1945, the original justification for the project was gone, but the momentum was just too great. The investment, the secrecy, the sheer scale of it, it just kept going.
And the new focus became ending the war in the Pacific.
Which led, of course, to the only time these weapons have ever been used in war. Hiroshima, August 6th, and then Nagasaki 3 days later.
A moment of incredible scientific achievement, immediately followed by this profound moral crisis.
You see it perfectly in Robert Oppenheimer's reaction. After witnessing the first test, the Trinity test, he recalled a line from the Hindi scripture, the Bhagavad Gita.
Now I am become death, the destroyer of worlds.
Yes, and that single statement captured it. This wasn't just a new bomb, it was a tool for potential self-annihilation. It introduced a moral weight, a moral cost that humanity has been grappling with ever since.
And that moral abyss leads us straight into the paradox of the post-war world. The technology was out there. Now we had to figure out how to live with it.
Or die by it. And the world immediately learned two completely contradictory lessons. And the tension between them defines everything that followed.
Okay, so lesson A, the positive one.
Lesson A is that the world saw what happened at Hiroshima and Nagasaki and collectively recoiled in horror. It created this powerful, unspoken nuclear taboo, a shared understanding that these are not just another tool of war, they are something else entirely.
And that taboo has held for almost 80 years, through countless other wars and conflicts.
It's a staggering achievement, really. The weapons are there, but the threshold for using them has remained incredibly high. But then there's lesson B.
The negative lesson.
The negative lesson, which world leaders learned just as quickly, was that you absolutely could not afford to be the nation that didn't have them. Falling behind was no longer an option.
So instead of disarmament, we got an arms race, a frantic escalation.
Exactly. The logic of self-preservation took over. The Soviet Union got the bomb in 1949, then the UK, then France, then China. The arsenals just exploded in size, all driven by this fear and the logic of deterrence.
You can't deter a nuclear attack without a nuclear weapon of your own.
That was the thinking. But this uncontrolled buildup, especially the atmospheric testing in the 50s, it created this huge global alarm. The radioactive fallout was literally circling the globe.
And that's what forced the superpowers to finally put some brakes on the race.
It did. The first step was the 1963 Partial Test Ban Treaty. It didn't stop development, but it pushed all the testing underground, which at least stopped the worst of the environmental contamination.
Okay, so you stop poisoning the atmosphere first. Then you try to stop the weapons from spreading.
Which brings us to the centerpiece, the 1968 Nuclear Non-Proliferation Treaty, the NPT. This is the grand bargain of the nuclear age.
What was the bargain exactly?
Basically, the countries that didn't have nuclear weapons promised not to build them. In exchange, the existing nuclear powers promised two things: to help the non-nuclear states with peaceful nuclear energy, and this is the crucial part, to work towards eventual total disarmament themselves.
So it was a promise of, we'll get rid of ours eventually if you promise not to build any new ones.
In a nutshell, yes. And it's been remarkably successful at limiting the size of the nuclear club. But the biggest reductions in the actual number of weapons came from the US and the Soviet Union talking directly to each other.
Right, the SALT and START treaties.
Exactly. At the peak of the Cold War, there were over 60,000 warheads in the world. An insane number. Through decades of these negotiations, SALT, the Strategic Arms Limitation Talks, and then START, the Strategic Arms Reduction Treaties, they managed to cut that number way down.
So what did those treaties actually do? What were they limiting?
Good question. The early ones, SALT, were mostly about putting a cap on the number of launchers, the SEBM silos, the submarine missile tubes, just stopping the growth.
Okay.
START went further. It mandated actual physical reductions in the number of deployed warheads and delivery systems. Both sides had to dismantle weapons and, crucially, allow the other side to inspect and verify that they'd done it.
And that's what brings us to the current number, which is around 12,000 to 13,000 globally.
That's right. A massive reduction. But let's look at how that number is distributed today. It tells you everything about the current balance of power.
And it's still highly centralized.
Overwhelmingly. Russia has about 5,450 warheads. The U.S. has about 5,170. Between the two of them, they still hold something like 85 to 90% of the world's entire arsenal.
So the stability between Washington and Moscow is still the central pillar of global security.
It is. But while they've been focused on managing that legacy Cold War arsenal, the strategic picture is shifting dramatically.
Towards Asia, towards China.
This is probably the biggest strategic change of the last 10 or 15 years. China is in the middle of a massive, rapid modernization and expansion of its nuclear forces.
What does that modernization look like, practically speaking?
It's a total overhaul. They're moving away from a small force designed just for a minimal counterattack. They're building hundreds of new missile silos in the desert. They're developing more mobile missile launchers that are harder to track. They're building up their submarine fleet.
So their arsenal is growing fast.
The pace is what's alarming strategic planners. Their total number is still much smaller than the US or Russia, maybe around 600 warheads now. But the speed of the buildup is what's changing the game. It creates a much more complex three-way dynamic that the world hasn't had to deal with before.
And China's rise obviously has ripple effects across the region.
Of course, you have these other very tense regional nuclear standoffs. The most obvious one is India and Pakistan.
Yeah.
They have smaller arsenals, less than 200 each. But they share a border, they have this constant flashpoint in Kashmir, and the time for a missile to travel between them is just minutes. Any conventional fight between them could escalate with terrifying speed.
And we should also touch on the alliance strategy. The U.S. arsenal isn't just for the U.S.
That's a vital point. Through NATO, the U.S. has a nuclear sharing policy. There are American tactical nuclear weapons hosted in countries like Germany, Italy, Turkey.
So it's a collective defense strategy.
It binds the alliance together. It says an attack on one is an attack on all, and the ultimate guarantee behind that promise is the American nuclear umbrella.
Okay, so we've cut the numbers, we have treaties, we have this taboo against use. But the danger is still very real. Why?
Because the basic logic hasn't changed. One, no one is actually disarmed. Two, the whole system is still built on deterrence, the idea that you keep the peace by threatening mass destruction. It's a permanent standoff.
And three, we have entirely new kinds of risks now.
Exactly. Cyber attacks on command and control systems, the possibility of hacking early warning satellites to create a false alarm, the risk of a technical glitch starting a war, the combination of thousands of weapons, the flawed logic of deterrence, and these new vulnerabilities. It means the risk of an accident is still frighteningly real.
Which brings us to the ultimate case study in how fragile this whole system really is, the Cuban Missile Crisis.
1962. It's the ultimate proof that you can stumble into a global nuclear war not through some grand evil plan, but just through miscalculation, bad information, and human stress.
The basic story is well known. The Soviets put missiles in Cuba to counter U.S. missiles in Turkey. For 13 days, the world held its breath.
But the key details are what's so chilling. You had American spy planes accidentally flying into Soviet airspace, triggering alerts. You had a Soviet submarine commander under attack with depth charges and cut off from Moscow, who was minutes away from launching a nuclear torpedo.
He stopped by another officer on board, wasn't he?
He was. Vasily Arkhipov. One man's caution prevented World War III. And that's the point. The crisis was solved not because the system of deterrence worked, but because it failed, and a few cautious humans stepped in at the last second to pull us back from the brink.
And that event exposes the fundamental flaw in the whole idea of mutually assured destruction, or MAD.
It does. Because the hard truth is, as long as these thousands of weapons exist ready to go, the chance of them being used is never zero. You can't eliminate a risk while you're holding on to the instrument of that risk.
And the doctrine of EBI itself rests on a very shaky assumption.
It assumes that everyone on all sides at all times will be perfectly rational, perfectly calm, and have perfect information. And we just know that's not how humans work, especially under the most extreme stress imaginable.
There's another incident, 2 decades after Cuba, that proves that point perfectly. The Stanislav Petrov story.
A perfect, terrifying example. September 1983. Petrov is the duty officer in a Soviet early warning command center. Suddenly, the alarms go off. The system says the United States has launched 5 ICBMs,
And protocol will be to immediately report that up the chain of command.
which would have almost certainly triggered a massive Soviet retaliatory strike. But Petrov, he hesitated.
He had a gut feeling.
He had a gut feeling. He reasoned that a real first strike wouldn't be 5 missiles, it would be hundreds. It felt wrong. He went against all protocol and reported it as a system malfunction, and he just waited.
And he was right.
He was right. It turned out to be a false alarm caused by a bizarre alignment of sunlight reflecting off high-altitude clouds that tricked the satellite sensors.
So the world was saved not by a multi-billion-dollar system, but by one man in a bunker who chose to trust his intuition over the machine.
It's a triumph of human judgment, but it's also a terrifying lesson. We're relying on having a Stanislav Petrov in the right place at the right time, making the right call in under 5 minutes. That's not a security strategy. That's just luck.
This gets to that common misconception you hear in movies, the idea of a 2-minute nuclear war.
It's completely misleading. That 2 minutes, or maybe 5 or 10, that refers to the decision window. The incredibly short time a leader has to decide if a warning is real and whether to launch a counterattack before their own command systems are destroyed.
It's the point of no return.
The point of no return. But the war itself would unfold over a much longer period.
Let's walk through that timeline.
Okay, so first you have that critical decision phase, minutes. A leader has to make an irreversible choice based on blinking lights on a screen.
If they say yes, the physical conflict begins.
Right. The initial strike phase. The missiles are launched. But even ICBMs take time to travel. We're talking 20 to 40 minutes to cross continents. That's when the first wave of destruction would hit.
And then comes the retaliation.
The retaliation phase. This would happen over hours, maybe even days. The most survivable parts of the arsenal, especially the ballistic missile submarines hiding in the oceans, would launch their counterstrikes. It would be a messy, cascading disaster.
So the explosions themselves are relatively quick, but the consequences, they last a lifetime or longer.
That's the horrifying reality. The physical blasts are over in seconds, but the global effects would last for decades. The biggest secondary effect would be nuclear winter.
Which is not science fiction. It's based on solid climate modeling.
It is. The massive firestorms in incinerated cities would pump enormous amounts of smoke and soot high into the stratosphere. That soot would block out the sun, potentially for years.
Causing global temperatures to plummet.
Exactly. It would cause crop failures worldwide, mass starvation, the collapse of ecosystems. The war might start in the Northern Hemisphere, but the famine would be global. It's the quickest war to start, but the longest war to end.
So knowing all that, knowing the system is fragile and the consequences are unthinkable, the question becomes paramount. Can we physically stop one of these things once it's in the air?
It's the natural question to ask, and we have spent trillions of dollars trying to answer it. But you have to get rid of the idea of some perfect, impenetrable shield like in a movie.
It's not a single shield.
It's a layered defense, a desperate race against time and physics with different challenges at each stage of the missile's flight.
Okay, let's take those stages one by one. First, the boost phase, right after launch. This is supposed to be the best time to intercept it.
In theory, yes. The missile is moving relatively slowly, and its huge rocket engine is burning like a giant flare. It's incredibly easy for our satellites to see.
So what's the problem?
The problem is geography and politics. In those first few minutes, the missile is still over enemy territory. Russia, China, North Korea. You can't just fire an interceptor into another country's airspace on the assumption that it's a hostile launch.
It would be seen as an act of war in itself.
It could start the very war you're trying to prevent. So it's technically the easiest phase to hit the target, but politically it's almost impossible to engage.
Okay, so the missile gets into space. It's now in the mid-course phase, coasting for 20 minutes. This is the main focus of our current defense systems.
It is. This is where systems like the Ground-Based Midcourse Defense, or GMD, come into play. The idea is to launch our own rocket, an interceptor, that literally collides with the incoming warhead.
The hitting a bullet with a bullet scenario.
Precisely. The interceptor is just a kinetic kill vehicle. It doesn't have an explosive. It just slams into the warhead at hypersonic speed.
But this is where the offense has a huge advantage, right? Decoys.
This is the Achilles heel of midcourse defense. In the vacuum of space, A heavy, dense warhead and a lightweight, inflatable decoy balloon shaped like a warhead travel at the exact same speed and on the exact same trajectory.
Because there's no air resistance to slow the lighter object down.
Exactly. So the attacking missile can release the real warhead along with dozens of cheap, simple decoys. And our radar and sensors have just a few minutes to try and figure out which one is the real threat in this cloud of objects.
And if you shoot at the wrong one,
You've wasted a multi-million-dollar interceptor, and the real warhead just keeps on coming. It's an overwhelming challenge.
So the final last-ditch chance is the terminal phase, as the warhead re-enters the atmosphere.
The last few seconds. This phase is all about extreme speed and no time. The warhead is plummeting, heating up from atmospheric friction, and it's almost at its target. Intercepting it here is incredibly difficult. There's almost zero margin for error.
So the hard technical truth is that missile defense isn't a guarantee. It's not a shield.
It's a mechanism for increasing odds. Maybe we can get the success rate up to 80%, maybe even 90% against a limited attack. But with nuclear weapons, 90% success is a total existential failure.
If 10 warheads are launched and you stop 9, the one that gets through still changes the world forever.
It destroys a city and, just as importantly, it triggers a full-scale retaliation. The game is over.
Let's talk about the warhead itself for a second. How does it actually detonate? It doesn't just explode on impact, right?
No, absolutely not. That's a huge misconception. These things are designed with incredibly complex and redundant fusing systems. They have multiple safety locks.
But what tells it when to go off?
It's a cross-referencing system. The fusing mechanism is constantly checking its altitude, its speed, the time of flight. And only when all those conditions are met, exactly as programmed, will it detonate.
And it's usually not meant to hit the ground.
Right. The most common type of attack is an airburst. The warhead is designed to detonate at a specific altitude, maybe a few hundred meters above the city.
Why do that?
It maximizes the destructive energy of the shockwave over the widest possible area. A ground burst would waste a lot of that energy just digging a crater. An airburst flattens more buildings and starts more fires.
And these complex safety systems mean that if our interceptor does hit the warhead, it won't cause a nuclear explosion.
That is a critical point. Hitting it will not trigger a nuclear detonation.
Wow.
It might break it apart, and you could have radioactive material scattered over a small area, a dirty bomb scenario, which is bad. But it is not the city-destroying nuclear yield. The goal of defense is simply to prevent that intentional, programmed detonation from happening.
The sheer difficulty of all this, the fact that even near-perfect defense isn't enough, it really makes you question where we're putting our energy and our resources.
It's where the conversation has to shift, away from pure engineering and into philosophy, into policy. The engineer's dream is always to find the perfect technological fix. Maybe some new electronic warfare that can jam the warhead's guidance system.
But why is that so difficult with these specific weapons?
Because of that redundancy we just talked about, these warheads are hardened. They're designed to survive a hostile electronic environment. You can't just fool one sensor. You have to fool the entire integrated system, the altimeter, the timer, the accelerometers, all at once. It's practically impossible to guarantee.
So if the technological shield will always be leaky, where should we be focusing our efforts for real security?
The most realistic and vital area is what you could call decision security. We have to accept that the best strategy isn't stopping the projectile, but preventing the launch in the first place.
Cutting the path to war.
Exactly. Investing in technology that eliminate false alarms. That extends a leader's decision time from 5 minutes to 5 hours. That automates crisis communication so adversaries can actually talk to each other clearly when things are going wrong.
So better brakes, not just faster bullets.
Perfectly put. We need to manage the human factor, the panic, the mistrust, the potential for error that will always be there when humans interact with this technology.
Let's use a thought experiment to really drive this home. Let's say humanity succeeds. We build a colony on Mars, a fresh start. Are they safe from nuclear weapons on Earth?
Well, the immediate technical answer is yes, they're safe, but only because of physics. An intercontinental missile travels for 30 minutes. An interplanetary journey takes months. Our current weapons simply can't do that. Mars is safe because of distance and logistics, not because of some fancy Martian shield.
But that's just a temporary physical barrier. It doesn't solve the real problem, does it?
It's the perfect philosophical pivot. Because if we ever get to Mars or another star system, we will take our human nature with us. Our tendency for conflict, for competition over resources, for fear of the other.
The same dynamics that created the arms race on Earth would just be replicated on a new planet.
Inevitably, we would just invent new weapons tailored for that environment. The conflict is portable. The problem isn't the missile, it's us.
And that leads to what you call the ultimate nuclear paradox.
I think so. Humanity has achieved incredible technological maturity. We have the power to annihilate ourselves. But we have not yet achieved the corresponding ethical maturity. We don't have the collective wisdom to manage the power we've created.
Progress without morality is just accelerated risk.
That's it exactly. And it means the true shield, the only shield that can ever really protect us, isn't a piece of technology.
It's a shift in human consciousness.
It has to be. The ability to manage our own fear, to choose cooperation over competition when the stakes are this high. The nuclear dilemma isn't an engineering problem. At its very core, it is, and always will be, a choice problem.
And as long as humans are making the choices, the risk will always be there.
We've covered a lot of ground today, from the physics of the atom to the fear in the minds of the Manhattan Project scientists, all the way to the flawed, leaky reality of missile defense. And I think the one lesson that stands out is that the technical difficulty of interception just underscores one central truth.
That prevention is the only real path to survival.
It has to be. Sober, clear-eyed human choice.
We looked at the numbers, the 12,000 warheads still out there,
Yeah.
the new complexities from China's rise, and we acknowledged that even with all our treaties, we're still relying on the assumption that everyone will act rationally. An assumption that a man named Stanislav Petrov proved was almost fatally wrong.
History shows us that we do often step back from the edge. The Cuban Missile Crisis is the prime example. But relying on luck, or the last-minute caution of a few good people, is an incredibly poor strategy for long-term species survival.
So we'll leave you with a final thought to mull over. If this is all, at its root, a choice problem, what specific, tangible conditions do we need to create to make it more likely that humanity consistently makes the right choice? Whether it's in how we train our leaders or how we build our communication systems. How do we engineer a system that favors de-escalation and cooperation instead of just relying on fate?
That's the real work, isn't it? The world isn't truly safe until the human mind is safe from its own worst impulses.